All right, students, today we're going to start our chapter on circles. In the first section that we're going to go over, notes 10.1, we're going to use the properties of tangents. So, to understand that concept better, we need to review some vocabulary and some properties of circles. Okay, so first of all, the set of all points in a plane. Okay, so it's in a plane, it means on this flat surface, which are equal distance from a given point. So if I'm given this point here, and this far, and I go this far all the way around, all of these points here, every single one of the points that are on here, that makes up a circle. Okay? The point from which all points of the circle are equidistant. Okay, so this point right here, the beginning point where all these points are equidistant from, that's called the center. A segment from the center of a circle to any point on the circle. So we have from the center out to the point on the circle, that's called the radius. A segment whose endpoints are on the circle. Well, I see two segments. I see this segment and this segment, but it didn't tell me anything special about that segment, so it's just a segment where the two endpoints are on the circle. So that is called a chord. The next one says a chord that contains the center of the circle. Okay, so here again, this is a chord, but it's special because it goes through the center. So it's here and here. That makes these 2 points make it the chord. Going through the center makes it the diameter. A line that intersects 2 points. So we need a line. Here's a line. It's going through the circle, and it's going to touch the circle at 2 points. That's called a secant. A secant line. All right, and then we have a line that intersects the circle in exactly 1 point. So here's this line, and it's intersecting at that 1 point right there. That's called a tangent. And that's our focus for today, is tangents. Okay, so okay, now you see that we don't have any more vocabulary left, but we still have this right here. That's pointing to that dot. That dot is where the line is tangent to the circle. So we call this point right here the point of tangency. All right. Now let's go to page 2. In page 2, we have some theorems. Our first theorem is talking about a tangent, and in this theorem it says, in a plane, a line is tangent to a circle if and only if, so that means it goes both directions, the line is perpendicular to a radius of the circle at its endpoint on the circle. Okay, so we need to highlight some of the features here of this theorem. First of all, I'm going to highlight the tangent. Point out that that's this line right here, the one on the outside of the circle. Okay, and I'm going to highlight the word perpendicular because here we have to either prove that it's perpendicular or it has to be given to us that it's perpendicular. Okay, and then perpendicular to the radius of the circle at its end point. That end point, that's that point of tangency again that we're talking about. Okay, now the only word I didn't highlight here is the plane. And this one right here, it just means that it can't be a three-dimensional figure that we're talking about. We're talking about a circle, or we're talking about a flat plane surface. So think of your piece of paper as the plane. All right, next. The next theorem says tangent segments. Now we've been introduced to tangents as lines, but now we're talking about the concept of the tangent being a segment. So if you notice here, I have these lines, but I'm going to highlight the section that is the segment that we're talking about. So here from point H to point K, we're talking about this segment, which is part of this tangent line, and we're talking about this segment here from H to J, which is part of this tangent line. So these are called tangent segments. All right, from a common point, there's my common point, okay, and what do we know about these two segments? Well, if they're indeed tangent and they intersect at that one point, then that segment right here is going to be congruent to this segment right here. So the tangent segments are congruent. All right, let's do some examples. The first example is this graph. Find the radius and the diameter of the circle. Well, to find the radius and the diameter of the circle, it's easier if I know where the center is. So if you look here, you have all of these segments. Segment from here to here, segment from here to here, here to here, all of these segments. So you have to look very carefully and find out which is the longest one. And that would be this one right here. That is a diameter. Okay? And you do it this way, and you'll see that this is the diameter. Okay, so the center is going to be where two diameters intersect. That's going to be over at 1, 2, 3, 4, up 1, 2, 3, 4. So that's at point 4, 4. And now it's very easy to count and find the length of the radius. So here, that's going to be from the center out, 1, 2, 3, 4. So that's 4 units. And the diameter, of course, would be from one side of the circle to the other, so that's 8 units. All right. Check for understanding. Use a diagram to find the given lengths. You have two circles here. You have circle A in blue, there's the center of the blue one. And then you have this, you had circle B first, that's the blue one. And then this right here, that's the center for this one right here. So if you make them different colors, it'll be easier to answer these questions. But I want you to find the radius of circle A, the diameter of circle A, the radius of B, and the diameter of B. And make sure you bring that in when you come in. And notice how I put labels, so you need to put labels as well. All right, next page. On the next page, we have an example that's asking us to verify a tangent to a circle. Okay, so first of all, it says in the diagram RS is a radius of this circle R. Is ST tangent to circle R? Okay, so in order to prove that this is tangent, we must prove that this line right here is perpendicular. We need it to be perpendicular to the radius at point S. Well, we don't have anything indicating that it is perpendicular. Let me erase this because we don't have that given to us. We need to be able to prove that. Okay, so facts. We want to be able to prove that if, here's the first fact, if ST is tangent, then it is perpendicular, maybe that's a perpendicular symbol, to RS. All right, so that's one fact that we know that we're going to have to prove. All right, well, if it's perpendicular, then that makes a right angle. And if that's a right angle, then that makes this triangle a right triangle. Okay, so if ST is perpendicular to RS, then angle RST is right, or is a right, should put the word a, is a right angle, and triangle RST is a right triangle. Now, some of you may already know where I'm headed with this, but we don't know that this is a right triangle. We need to be able to prove that it's a right triangle. Way back a couple of lessons ago, we had a test called the type of triangle test. Some of you may remember that that was the Pythagorean theorem backwards. We inverted it. We have to put the C on the left, big giant circle, C squared, big giant circle, A squared plus B squared. And remember, if the equal sign goes in the circle, that means that we have a right triangle. And just to finish out the test, we don't need any other information, but just to remind you that if it's greater than, then it's obtuse. If it's less than, then it was acute. Okay, so we want to fill in the information here to our test, and we want that to be an equal sign there. All right, so I'm going to set up my test. That's going to be the longest side. C is always the longest one, so that's 26. 26 squared, big giant circle, 24 squared, plus 10 squared. What we're doing is we're trying to figure out what these values are. Plugging 26 times 26 into my calculator, or 26 squared, I get 676. 24 squared is 576. And 10 squared is 100. Okay, so since we have 676 on the left, and then add those two together, we get 676 on the right, we know that that's equal. Therefore, we know that that is a right triangle. So this right here tells us that triangle RST is a right triangle. Well, because that's a right triangle, that tells us that ST is perpendicular to RS. And then from there, we know that ST is tangent to circle R. Okay, folks. That's how you prove that. So this over here, this right here, is the work that you need for this one here. So when you're doing your check for understanding, I'm going to expect you to test it, and then if it is, you need to tell me that because the triangle is a right triangle, because those two are perpendicular, and because therefore this is a tangent to the circle. If it's not, then all you have to do is tell me that it's acute or obtuse, and therefore not a right triangle, so it can't be tangent. Okay, now let's talk about tangents. Common tangents. Draw a line that is tangent to both circles. Okay, so that means it's going to a line that touches the circle, each circle, at just one place. Okay, so here, right there, if I put a line right there, it touches this circle and this circle at that point right there. All right, here's another one. Tangent here and tangent here. Okay, and then here's another one. Oops. Tangent here and tangent here. Okay, so in this example A, there are 3 tangents. 3 common tangents. All right, let's look over here. This one, I have 1 here. I have 1 here. I have 1 here. That's tangent here and here. And then I have 1 here. It's tangent here and here. Okay, so that means that I have 1, 2, 3, and 4 tangent lines, 4 common tangents. Let's take a look at this one. Now, in order for a line to be tangent to this little circle, it's going to go through the circle. So it's tangent to the small, but it's a secant to the large. So that means that there are 0 common tangents because this is not tangent to both. Common tangents means it has to be tangent to both circles. All right, the next one. Check for understanding. Tell how many common tangents the circles have and draw them. So you're doing basically the same thing up here to these right here. Okay, make sure you do those and bring them in. That's your check for understanding. All right, last page. Okay, applying the theorem. Here we have that tangent segments theorem. So it says QR is tangent to circle C at point R. And QS is tangent to circle C at point S. So that makes Q their common tangent, a common point, or their point of intersection. So since there are 2 tangents that intersect at this common point, then that means that this segment is congruent to this segment. So what we know is that QR is congruent to QS. Okay, well, that just means that QR equals QS. QR, we know, is 32, so I'm going to put 32 here. QS is 3x plus 5. So now I just use my algebra. I'm going to subtract 5 from both sides. I get 27 on the left equaling 3x on the right. Divide both sides by 3. I get 9 equals x. So I found my value of x. Check for understanding. You're going to do the same thing here. And that is it for Notes 10.1.